Happy Saturday, scientists. Let's review. We begin a new subject today, physics. There are plenty of things to get us charged up, and current events in physics have sparked many a revolution. All right, I will stop with the terrible puns, but on with the physics. E1 is once again all about particles, and once again we're starting off with the atomic model. I'd like to go through a bit more details of some of the scientific discoveries this time, to make sure that you know them, but this does come up both in chemistry and physics, so you should be pretty familiar with it already. Dalton's central premise was that the atoms of an element are the same. So any hydrogen atom would be the same as any other hydrogen atom. His second point was that the atoms of one element are different to those of another element. Next, we go on to J.J. Thomson. He was looking at the rays that are given off by hot metals The rays he was studying in particular were the cathode rays, and he found that these were formed of particles that were very, very small. And so he called these new particles electrons. Next, we move into the grand old gold foil experiment by Geiger and Marsden and sort of Rutherford. In this experiment, they were trying to prove Thomson's plum pudding model. And so if we look at what the model would have been, you've got a beam of alpha particles coming through, and you have a sheet of gold foil. And then all around that sheet of gold foil, you've got a detector. You would expect, if Thomson is correct, that these alpha particles would pass through. So that's what you would see if Thomson was correct. However, instead of having that, what we had is some particles being deflected kind of completely back, and some just sort of being deflected to the sides. And what that indicated is that something else was going on. It indicated that there was some sort of dense nucleus had to be present. A quote from Rutherford that I really like is that it was as if we fired a shell at a piece of tissue paper and it bounced back. What he was able to do is to come up with this Rutherford model, that we had some sort of dense positive nucleus with most of the mass, if not all of the mass, of the atom. And then there were those tiny little electrons sort of whizzing round the outside, kind of like planets round a sun, but not at any particular space or angle or level of energy. What Bohr realized is that if you have an electron with a negative charge and a nucleus with a positive charge, there would be an attractive force between those two, and that would kind of collapse everything down and in on itself. Because the universe hadn't collapsed, he realized that you had to have the nucleus, and the electron had to be moving kind of with enough speed and enough energy not to be pulled into the nucleus. And that's what gave Bohr his energy levels. And we now know that there's one energy level per row on Mendeleev's periodic table. Now that we know all about particles and how they fit together, we move into the material properties of the atom. And we begin with density, which is a way of measuring how much mass is in a given space, or a given volume, or how many particles essentially are in that volume. And so the formula for this is that density is equal to the mass divided by the volume. And this can be done in a number of different ways. You can do it in grams per milliliter. And we know that the scientific units are grams per centimeter cubed, because a centimeter cubed is equal to a milliliter. You may also see density given to you in kilograms per meter cubed as well, depending on the table that you're taking your measurements from. When you're doing your density calculations, make sure you remember your volume formulas for shapes and make sure that you use the correct units so that they match up. The next point we get into is the concept of energy versus temperature. Energy is a measure of the total energy. We're talking all of the energy that is there. And it will depend on the arrangement of the particles, as well as their movement. By contrast, the temperature is only a measure of the average kinetic energy of those particles. And that leads you into those classic examples of having sort of a swimming pool full of water, and that's going to have more energy than, for example, a cup of tea, which would have more temperature. So the swimming pool might be at 20 degrees Celsius and the cup of tea somewhere in the 90s, but because the swimming pool has more particles, it has more total energy. This is related to the concept of specific heat capacity, which is a measure of how much energy a substance can absorb. 1 kilogram of substance specifically can absorb before its temperature changes by 1 degree Celsius or Kelvin. And so when you're calculating with specific heat capacity, the formula you're using is that energy is equal to the mass of substance that you're heating or cooling multiplied by its specific heat capacity multiplied by the change in temperature. Remember that the Greek letter delta means change. Delta T means change in temperature. Delta subject would mean change of subject. And speaking of a change of subject, specific latent heat. This is related, but it is the energy needed to break the bonds to change state. Or, if you're cooling a substance, then it would be forming bonds. Again, this depends on the mass of the substance and on its specific latent heat. And this is divided into 2 categories. You have the specific latent heat of fusion, which is going from solid to liquid or back the other way. And you have the specific latent heat for vaporization, which is where you're going from a liquid to a gas or back the other way. The final concept that we need to remember is about gas pressure and temperature. We need to remember that pressure is the collisions on an area with the particles. And if it depends on the collisions, then we know that we're going to need to look at the speed of particles. We know that temperature is the average kinetic energy, so that would mean that if we increase the temperature, the speed of particles is going to increase, which would logically mean they're going to collide more. And so you can have a graph of temperature versus pressure. What you then might be asked to do is to extrapolate backwards in terms of your temperature in order to find where there is zero pressure. This point is known as absolute zero, and it's minus 273 degrees Celsius, or 0 degrees Kelvin. And that is when all motion has stopped. If you're converting between Celsius and Kelvin, you may find it helpful to do yourself a number scale, with Kelvin on one side and degrees Celsius on the other. 0 Kelvin is minus 273 Celsius, 0 Celsius is 273 Kelvin. This will help you to place your numbers accurately on the scale and to do the conversion properly between those two temperature scales. P1 is rather a short topic in terms of content, but it really starts to underpin the other concepts in physics. It relates back to some concepts in chemistry, and of course it starts you out on those calculations that everyone loves so much for physics. So make sure that you're remembering your formulas, that you're practicing them. There's a worksheet in the description that can start you off on the right path for that, but more materials are available if you need them. And of course, have a lovely week sciencing. We'll see you next Saturday.